Hey folks, welcome to this episode on electron configuration. So we looked at orbital filling diagrams, or orbital diagrams, and there's just got to be an easier way. That's just takes way too much time to fill all those electrons into those little boxes to show the configuration of electrons. And sure enough, there is something called electron configuration. And basically it's a notation that provides the same information as that orbital diagram, but instead of drawing boxes and arrows and showing energy and whatnot, we just actually write numbers and letters. So you can see over here, just below, here's our orbital diagram for hydrogen. Very simple. Hydrogen only has one electron, so we're going to put it in our 1s. And our electron configuration actually represents this drawing in this numerical and alphanumeric system. So the number 1 represents the energy level 1. The S represents the orbital type, so we actually already have that information there. And then this superscript number actually identifies how many electrons are in that orbital. So in this case, I only have one unpaired electron, so it's going to be 1s1. That's it. So we have our principal quantum number over here, our angular momentum number, which is going to be our L's representing our subshell type, and then how many electrons are actually found in that orbital. So let's look at phosphorus, for example. We know that phosphorus has 15 electrons, so if we were to ask to draw the actual orbital filling diagrams, we know we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So there's our orbital diagram for this. We can see that we have pretty much everything paired electrons, except we have 3 unpaired electrons over here in our last shell. So how do we translate this into electron configuration notation? Well, we have 2 electrons in our 1s, so it's going to be 1s2. Then we have 2 electrons in our 2s, 2s2. Now here, when we have our 2p, we're going to have 2p, and we have 6 electrons altogether. So we're going to have 2p6. Then we go into our 3s, and we have 2 electrons there. It's going to be 3s2. And finally, when we look at our last one over here, our 3p, we have 3p, and we can see that we have 3 unpaired electrons. So it's going to be 3p3. That's it. So when we look at the configuration and the periodic table, there's actually a very nice relationship between the two. Now, the periodic table is kind of arranged in the way that electrons are going to fill these orbitals, and it's broken up into blocks to show how these electrons basically fit into this atom. So here, when we look at this, we can see that our metals, our alkali metals and our alkaline earth metals, are going to be forming our S block. So here's this case, our S block. Now be careful, we also have a little bit of that S block over here, and that's going to be your helium atom there. Our transition metals are going to be our D block. These ones over here, kind of starting from boron and going into neon over here, this is going to be our P block. And then finally, these kind of transition metals here, the inner transition of the rare earth metals, they're going to be our F block over here. So when we have elements that, for example, fit over here, if we said this is going to be chlorine, for example, we know that its valence electrons, its outer electrons, are going to be in the P block. And because it's also in row number 3, it's going to be in the 3p orbitals. Okay, so remember that the period number, the ones going from left to right, show the energy level. Our group numbers this way show the number of valence electrons. And then when we look at the types of subshells, we can look at which block that electron is going to be found in. So this is another way of visualizing it here. It's a nice way of kind of looking at it in a different way. Here we have our 1s, so you can see that we have our 2 elements, hydrogen and helium. Our 2s, which exists as going to be lithium and beryllium. We kind of have to cross the ocean into our 6 elements there, which form our 2p, and then we keep going and going and going. This is a nice little reference, so I strongly encourage you to print this out. It also shows some of the anomalies that we spoke about before. So again, when we want to do this configuration using our periodic table, we have to find our elements in that periodic table, and then move through all the blocks left to right, filling all the orbitals until you reach that desired element. Remember, that kind of follows the Aufbau rule, where, let's say if our element was over here, we actually have to fill our lowest before we can actually fill that element that we're looking for. So you'd have your 1s2s filled, then you have your 2s2s filled, you have your 2p6 filled, 3s2, and then your 3p. If the element was here, it'd be 1, 2, 3, 4, it'd be 3p4. Okay? This is a nice little diagram, shows the relationship between that and that. Okay, so let's look, if we had to do the electron configuration for chlorine without using any orbital diagrams, just using our periodic table, how would we do it? So the first thing is we have to identify where chlorine is. So chlorine is right over here, okay? So what we know is that its valence electron, its outermost electrons, are going to be, well, first of all, this is 1, 2, and 3. It's going to be in energy level number 3, and the last electron to be placed is going to be in this block over here, this green block, and we know that this green block is going to be P. And chlorine is also the fifth element in the P block. Here we have aluminum, which is number 1, silicon, phosphorus, sulfur, and chlorine. So I'm going to predict that my last little part of my electron configuration is going to be 3p5. Why? Because it's in row number 3, it's in block P, and it's the fifth element in that block there. Okay, so what we have to do is we have to go through every single element to get to chlorine. So we have to make sure that all of those are filled. So first things first is that here we have 1, and remember that this is going to be your S block. The other part is continuing over here. So we have to make sure that this one is filled. So I know I have my 1s. I have to make sure it's filled. The maximum amount of electrons that can go into an orbital is 2, so it's going to be 1s2. Now after I fill this one, I'm going to go to the down one, and the first one over here is going to be my 2. This is part of my S block, and I have to make sure that that's filled. There's 2 spots there, and can only hold 2, so it's going to be 2s2. Now after I fill this one in, kind of jump across the river and go into this. Now you can see that this is shown by a different color. The periodic tables you're probably going to deal with don't have different colors, so you have to recognize that this is now the P block. It's still in row number 2, but it's the P block. So it's in row number 2, and it's the P block, and I have to ensure that this is filled before I can move on. I have to move on because I'm not at chlorine yet. So to fill it, I have a maximum of 6 bases, 1, 2, 3, 4, 5, 6. So this will be 2p6. Now just kind of an aside, remember that P is L is equal to 1, and ML is going to be -1, 0, and +1. So each P orbital has 3 orientations, the px, py, and pz. Now remember that each one of these can hold a maximum of 2 electrons. So how many electrons can the P hold? Well, 2, 2, and 2 for a total of 6. Where does that 6 come from? Well, right there. 1, 2, 3, 4, 5, 6. So let's go back. So after we fill this over here, we go to the next one, which is going to be in the third period, and it's in the S box, so 3s, and we have to make sure it's filled, so the maximum it can hold is 2. And then finally we jump across over here. We get in again, still in row number 3, but now we're in the P section, and chlorine is right over here, but we have to 1, 2, 3, 4, 5, so we get 3p5. Look at that, we got the same last configuration. So remember that we have to fill in all of our lower energy levels before we can get into our higher one there. Okay. Just kind of a kind of reminder that here are our valence electrons. This is still your level 3 or energy level 3. So this will be your valence electron. They are split up into 2 different subshells, but these are going to be your outermost electrons. If you remember kind of doing a Bohr-Rutherford diagram of in this case chlorine, you'd have your first energy level filled with 2 valence electrons. Your next one would be 1, 2, 3, 4, 5, 6, 7, and 8. So that would be, your first 2 would be this, then your 8 would be these over here, and then finally you would have your electrons, which are going to be right over here. You would have 1, 2, 3, 4, 5, 6, 7, and 8, and those are your 8 electrons over there. So you can see that in the kind of this Bohr-Rutherford diagram, you still have those 8 electrons, even though they're in the S and P split up, they're going to be your outer electrons. Okay. Now there is even a more simple way to doing this. If we look at potassium and we did the electron configuration for potassium, again potassium, we first have to find potassium is going to be right over here. I know it's very small to see. So that's going to be in row number 4. It's in the S block, and it's the first element into the S block, so it's going to be 4s1. So we actually have to make sure that it's filled, so we have to go through all of these different ones. I'm going to go 1s2, 2s2, 2p6. How did I get there? So remember, 1s2 has to be filled. 2s, row 2, block S has to be filled, so s2. Then I jump across into 2p, 1, 2, 3, 4, 5, 6, 2p6. Then I go into my 3s, that has to be filled, so 2, and then 3p6. So when I have my 3p6 over here, so 3p block, 6 electrons, that's my 3p6, and then I go into my 4s block, and there's 4s1. So that would be my electron configuration for potassium. Now there's actually a better way, maybe not better, but a little bit easier. If we actually look at this, all of these electrons equate to argon. Okay, so if we were to do argon, we'd have 1s2, 2s2, 2p6, 3s2, and then since argon is the last one, it would be 3p6. So actually, if we use our noble gas as a kind of condensing point, all of this would be equal to argon. So what we could do is we'll say, you know what, let's put argon into square brackets and start from there. So what I'm effectively doing is I'm getting rid of all of this notation and representing it in the noble gas in square brackets. And then what's left over is 4s1. That's it. So this is called the noble gas core configuration, where we use our noble gases as starting points and we put them in square brackets representing all of this electronic configuration. Now, you can't, what a lot of people do is say, well, if I want to find the electronic configuration of neon, shouldn't it just be bracket Ne if we use our gas core? No, you have to use the noble gas prior to that element. So when we look at neon, the noble gas prior to neon is actually He. And then from there, what we do is we continue on our electron configuration. So remember that this basically shows He. So what we'd do next is we'd put that in square brackets, and then we would put our next remaining stuff there, which would be 2s2. There's 2 electrons in our 2s orbital, and then 2p, we have 6 electrons, so we'd have 2p6. So this is not right. However, this is correct for neon. Okay. If you wanted to do the whole gas, if you wanted to do the whole noble gas configuration, it would just be 1s2, 2s2, 2p6. Now, again, this noble gas core for this kind of short doesn't really do much, but when you get into things like, for example, if you wanted to look at the electronic configuration of osmium, which is 76 on the periodic table, you don't really want to do all the electronic configuration before then. You could just start at xenon, put xenon in square brackets, and then continue on from there. All right, so here's some practice. What we'd like you to do is provide the orbital diagram, the electron configuration, and the noble gas core notation for an oxygen atom in the ground state. Okay, so work on this, pause the video right now, and when you're done, unpause and we'll have the answers for you. Okay, pause the video now. Welcome back. So here are the answers for this. Again, oxygen has 8 electrons, so that means that you're going to have 2 in the first 1s, then you're going to have 2 in the 2s, and you'll have 4 in the 2p. So this orbital diagram will get translated into 1s2, 2s2, and 2p4. Again, if you wanted to use the noble gas configuration, or noble gas core, you can translate this one into He, so kind of move that into He, and then right on from there. So 2s2 and 2p4. Now again, when we look at noble gas core for ions, there's not really much of a difference. When we look at sodium here, we can translate this into an electron configuration, which is going to be 1s2, 2s2, 2p6, and 3s1. Okay, so we have that unpaired electron there. And a noble gas core here, what we can do is when we look at sodium, the noble gas prior to sodium is not helium, it's actually neon. So what I could do is I'll put neon into square brackets and then write 3s1. When sodium loses an electron and becomes a cation, you can see that the electron configuration changes, and it actually changes to an electron configuration of neon. So what we have to do is remember that we can't just put neon in square brackets. We have to use the noble gas prior to neon. When we look at the electron configuration, it's going to be 1s2, 2s2, and 2p6. And you can see that that last outer shell is now full, representing neon. So what we have to do is we have to put our square brackets around helium, which is the noble gas prior to neon, and continue on from there, 2s2 and 2p6. What we do is we call this sodium ion isoelectric to neon, because it has the same electron configuration as this noble gas neon. It's not neon. Remember, it still has more protons, and that protons, the 11 protons, makes it sodium. But in terms of the electronic structure, it's very similar, in fact, the same to neon. Okay, so do some practice here. For a typical aluminum cation, remember there's underlined for a reason and bolded cation, fill out the following. Okay, so take a few moments, finish this up, and come back when you're ready to check your answers. So go ahead, pause the video now. Great, so the key word there was cation, and when aluminum forms a cation, it actually loses 3 electrons to become Al3+. So the atomic number for aluminum is still 13. It shows that it has 13 protons. However, when we look at the number of electrons, in a non-ion or just a regular standalone aluminum atom, you would have 13 electrons. But because it's lost 3 electrons to become 3+, it's going to be 10. Now, when we look at this, which standard atom also has 10? That's going to be neon. So when we look at that, it's going to be isoelectric to neon, and neon is in period number 2. So period number 2 relates back to the energy levels, so it's going to be number 2 as the answer there. Now again, it's the group number of the isoelectric element. Well, it's isoelectric to neon, and neon is in group number 8A, so we're going to put that over there. Now some periodic tables might go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 etc., into 18 over here. But generally, they're split up into the A elements and the B elements. And so here you have 1, 2, 3, 4, 5, 6, 7, and that would be 8A. The number of valence electrons, well, because it's in group number 8, it's going to have 8 valence electrons. Remember that the group number and the number of valence electrons coincide with one another. The subshells of the valence electrons will be found, and remember that the valence electrons are in this whole energy level. It's not just the p, so it's going to be 2s and 2p. And electron configuration, it's going to be the electron configuration of neon, because in this case the aluminum ion is isoelectric to neon. It's going to be 1s2, 2s2, and 2p6. And if we want to do that, we'd use the helium for our noble gas core and continue on there, 2s2, 2p6. Alright, thanks very much for watching. See you soon.